Hello! It is Tuesday again. And I'm not ready for it. Okay. So we left off in fractions. We just started scraping the surface on fractions. We actually have quite a bit to do as far as fractions go. Nicely done. Oh, everything's just working out right now. So yeah, we just got done with basic fraction work. That was finding prime numbers and divisibility. This is an essential skill for understanding fractions as a whole, pun intended. Going forward, we are on the next bit, factoring whole numbers. And so we have fraction basics, simplifying fractions before we even get to multiply fractions. So bear with me. And it's hot outside. I don't know about y'all, but it's like 100 degrees out there, 100 degrees Fahrenheit, mind you, out there. Whew. So, going forward, we are factoring whole numbers. So, finding the factors of a number. We pretty much know this. So, if we were given the number 10, we know a factor is 2 and 5, or 1 and 10. Either one will work. Going forward, even though this will work, anything with the 1, it's nice to know, but it won't be useful. So we are just looking for values other than itself and 1. So if we're given the number 21, that would be 3 and 7, otherwise it would be 1 and 21, and so on. So we understand that these are, we can find the factors going down the list if we go for, like we did. So we find, let's say another example, 35. 1 and 35, 2 does not fit, 3 does not fit, 4 does not fit, 5 fits, 5 and 7, 6 doesn't, 7 does, and it comes back to 5, so these would be the factors of 35. Now, finding factors of other numbers, I know these have been pretty simple. This is all that's been the factors of. But if we get a number such as 72, well, we can go 1, we can also go 2 times 36, 3, yeah, it's 24. So 2, 3, 4, and so on. So we get, so 72 divided by 4 is 1. Pretty sure that's 18. Yeah, 18 is 32. 32 plus 40. Yeah. So 4, 5, 6 does. 7 does not. 8 does. And 9 does, and that just comes back around. So these would all be the factors of 72. Now, a nice little notation you may have for finding the factors of this. So the factors of 72 are the set of 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and of course 1 in itself. However, that's not part of what we're looking at today. It's nice to know, but it won't be useful for where we're going. So one more example we have is 42. So we know 1 and 42, 2, and I wrote these in ascending order. That's nice and neat, especially when you're having to compare it to someone else's factors, some other numbers factors. But here, you can just write it from left to right as normal. So 2 times 21, 3 times 14, 4 does not fit in here, 5 does not fit in here, 6, and 7, and then 7 comes back around. So that's what you have. So finding the factors, not so difficult. So another way to do it, let's go back to that 72. If you know that 72 and 30 is divisible by 2 and 36, you can write it in a tree form. So at the top of the tree, we have 72. We're breaking it down between 2 and 36. Well, then what breaks down into 36? We have, you can have 9 and 4, 6 and 6. Whatever immediately comes to your mind, that's what you use. So we're going to go with 6 and 6. And each of these, what fits into 6 would be 3 and 2. And these don't break down anymore. They are prime. So then you have 2 and 3. And I'm pretty sure if you were to multiply 2 by 2 by 2, 2 by 2 by 2, times 3 times 3, 2 times 2 is 4, times 2 is 8, 3 times 3 is 9, 8 times 9 is 72. It comes back, even though it does not come back the same way that we broke it apart. It's kind of cool. This is kind of my favorite part about fractions, is that you can make whatever you need as you need it. So as these numbers that we got down to were 2s and 3s, 2s and 3s don't break down into anything other than 1 in themselves, and that will just keep going. And we're not, again, interested in that. So once we get to any prime numbers and breaking down a number, that's what we're trying to find out of factoring. So this is particularly called prime factorization. And the rule of this would be the fundamental theorem of arithmetic. Which states there is exactly one prime factorization for any composite number. So what this means, going forward, we're going to keep with that 72, and we just shown that 72 has the prime factorization of 2, 2, 2, 3, and 3. All of these multiplied together equals 72. Now we have 3 identical numbers in the prime factorization. Since they have to multiply to get to 72, we are going to write it in exponential notation for simplicity. No, excuse me, there are 3 to use. And it's super simple. If you see the same thing, that is the base, and how many there are is the exponent. So there are 2, and that is your prime factorization. Now what you could also do given an example like 60, is to find the prime factorization by dividing the number by a series of primes until the final quotient is a prime number. So how we would go about this, we understand that 2 is a prime number. So 60 divided by 2 is 30, no remainder. And then we would divide 30 by either 2 or 3, whichever we think would be the next available prime. Let's go with 3 because that comes out to a seemingly easy 10. And then 10 is still not prime, so 10 divided by 2, that's 5, with a remainder of 0. And 5 is prime. So you can do it this way too. So we have found the 2, the 3, the 2, and the last one is 5. So the prime factorization is 2 times 2 times 3 times 5, which in simplest terms is written 2 squared times 3 times 5. Personally, I prefer the tree method. It is much more intuitive. So if you have 60, you split that into 2 and 30. 30 can split into 15 and 2. 15 can fit into 5 and 3. And that's all the fruit you can get out of your tree. So then, again, you'd have 2 2's. So 2 squared times 1 3 times 1 5. And notice how the prime factorization of 60 does not equal the prime factorization of 72. That is back to the fundamental theorem of arithmetic, how there is exactly one prime factorization for any composite number. So let's assume, because assuming is kind of funny when you use it in a math way. It makes that out of you and me. So let's assume, just some prime factorization, 2 squared times 5 times 7. Let's say 2 numbers, we'll call them A and B, both equal this but do not equal each other. So we would multiply this out. Let's work with B. So B, 2 squared is 4 times 5 times 7. Now I'm not sure if I was ever clear. Signs of multiplication are the multiply by, the dot, multiply by, or if you get 5 times 7, that is also signs of multiplication. Just in case if you see these, they mean the same thing. So here, and I use the dot in between because it's much quicker to write with. I know you write however you need to write. Just know that this x, when you start to use variables, it'll start getting real messy. Because if you have x times 3, just because this is written way, way different than this, doesn't mean someone's not going to do this at some point. And that seems like you're either multiplying by 3 twice, but multiplying what? Notation is key. Use what is easily understandable. So we have B equal to 4 times 5 times 7. 4 times 5 is 20 times 7. 2 times 7 is 14. In the tens place, it would be 140. Now this means that A cannot be 140, but A does equal the 2 squared times 5 times 7. So we have 2 squared, which is 4, times 5 times 7. 4 times 5 is 20. And 20 times 7 is 140, which we have arrived to a contradiction. And this is a very layman proof because we assumed something to test a rule and shown that that rule is true. Because if two numbers have the same prime factorization, it turns out that they have to be the same number. So that is, no two different composite numbers have the same prime factorization. Et voilà. All right, let's go through a lovely example of finding the prime factorization of 234. Well, 234, we can see it ends in a 4. So that looks to be divisible by 2. 2 can fit into 2 once, 2 can fit into 3 once. With 1 left over, 14, so 17. Now, believe you me, I think. Nope. You know why? You know why? I think, therefore I am. But no, we went over this previously. So it's not divisible by 2 because it doesn't end in a 2, but it's divisible by 3. In fact, it's divisible by 9 because 1 plus 1 plus 7 is 9. So we have 9. So 9 can fit into 11 once, remainder 2, 27, 3. Now 13 is prime and 2 is prime, but 9 breaks down into 3 and 3. So the prime factorization is 2 times 3 squared, because there are 2 of them, times 13. Okay. Now, why this is all very important going forward? It's a very nice thing to be able to factor numbers, to break them down in an understandable way. That is because, let's say in this example, we have 2 numbers, 20 and 30, that we're trying to find common factors to. So finding common factors is where you find the factors of each. So the 20, factors thereof, 1 in itself, 2 and 10, 3 does not fit, 4 fits, and then 5, 4 and 5, and that completes what we know about the factors of 20. And just for clarity, just for niceness, we're going to write it in ascending order. So 2, 4, 5, and 10. And the factors of 30 are 1 in itself, 2 and 15, 3 and 10. 4 does not divide into 30 evenly. 5 does. 5 and 6. And 6 comes back around. Now we're going to do this nicely. Put it in ascending order. 2, 3, 4, 5, 6. 2, 5, 6. 10 and 15, which is just kind of seeing 2, 3, 5, 6, 10, 15. Now, finding common factors is merely looking at the list of each factors and seeing what's in common. So we have the 2, the 4. Oh, we missed the 5. I said there wasn't a 4. I don't know what I was looking at. So that is a 5. My mistake. It's a transcription error. So we have 2, nothing with 3, nothing with 4, 5, 6, 10, and 15. So they have 2, 5, and 10 in common. So from this, we'd like to find what is called the greatest common factor. That is a group of numbers that is the largest number that will divide each of the given numbers exactly. Greatest common factor is the greatest common factor of a group of numbers. This of is very important. That's why I was sounding a little confused. Of a group of numbers is the largest number that will divide each of the given numbers exactly. So between 2, 5, and 10, which are the common factors, the greatest common factor is this 10. So we will do another example. We are given the numbers 30 and 36. And the factors of 30 is 1 in itself, 2 and 15, 3 and 10, 4, 5, and 6. And that completes its set. 2, 3, 5, 6, 10, and 15. And 36, we have 2, 3, 4, 5, 6, 7, 8, 9. Because 6 times 6 is 36, 4 times 9 is 36, 3 times 12 is 36, and 2 times 18 is 36. So this is in proper order. I'm going to write it over here to be able to compare them a little easier. So we have 2, 3, 6, and I think that is it. So between 2, 3, and 6, 6 is the greatest common factor. I do believe so. I can give you a quick example as to why. So the question here is if your numbers were 30 and 60, (61) in itself, 2 and 30 is already here. Oh, I see. Okay, sorry. 2 and 30, you get 3 and 20, 4 and 15, 5 and 12, 6 and 10, 7, 8, 9, 10, and 10 is the end of it. 30, we have 1 in itself, 2 and 15, 3 and 10, 4, 5, and 6, and that comes around. So a great point here is that we have not been writing 1 in itself. This should have still been considered. This is one of those times that it matters. Yep, it mattered. So this also includes 1 in itself, into which they are both factors, and they are the greatest common factor between the two. Good point. Good point. All right, so stepping up from that, and we will continue going forward, putting 1 in itself in the factored list. We have another example of if we had the numbers 24, 30, and 36. So between the three of them, one at a time, 24 has the list of 1 in itself, 2 and 12, 3 and 8, 4 and 6, 5, and then 6 comes back around. And then that can be rewritten as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and all the way back to 24, 30. Now this does get a little monotonous, but very important to understand the process of how to get there. The reason why it's monotonous now is because it will be second-hand nature later. So we get 1 and 30, 2 and 15, 3 and 10, 4 does not fit, 5 fits, and 6 comes back around. So then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, and 30. Just nice and neat. And then 36, 1 in itself, 2 and 18, 3 and 12, 4 and 9, 6 and itself. 6 in itself kind of begins the rotation back. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 18, 36. Now, these are the factors between the three numbers. And just looking to compare, they all have 1 in common, they all have 2 in common, 3 in common. They do not all have 4 in common, or 5. They have 6, no 8s, no 9s or 10s, no 12s or 15s going forward. So 6 is the greatest common factor between these three numbers. One more example, just to kind of hit home the idea of finding the greatest common factor between three numbers. So we are given 16, 24, and 32. So 16, we have 1 in itself, 2 and 8, 3, 4 times 4 is 16, so that completes the cycle. And then we get 24. Before I write them out, I will go ahead and factor the rest of them. So 24, 1 in itself, 2 and 12, 3 and 8, 4 and 6, no 5s, and it comes back to 6, and that completes the circuit. And 32. Whew. 1 in itself, 2 and 16, no 3s, 4 and 8, no 5s, no 6s, no 7s, and it comes back to 8. So then, and if you'd like to write it this way, the longest one gets to go first. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 24. And then you can see where each of the next ones may line up. So 1 lines up with 1, 16 does not line up with anything. We're putting them in order. So we're going to go in order. So 1 and 2, 4 does not line, well, it does, but it does not line up with the 3. So 1, 2, 4, 8. The 16 doesn't line up with anything, so we can just put it here. And then again, we have 1 and 2 and 4, 8, 16, and 32, where nothing lines up with the 6 or the 3 or the 16, 12, 32, 24. But we do have 1s, 2s, 4s, and 8s, 8s being the greatest common factor. All right. So there is this, is to find all the factors of a number and compare them with other numbers to see which compared numbers are the greatest common factor. Another way is through the prime factorization. So we get the example, again, of 20 and 30, something we already know. If we find the prime factorization of 20, that is 2 times 2 times 5. And then if we find the prime factorization of 30, we know that is 2. See, 2 times 15, and 15 is 3 times 5. So we see that we have a 2 and a 5 in common. And these two are not common. How we discern the greatest common factor here is whatever matches, we multiply to get the greatest common factor. So the 2's match and the 5's match, but the 2 and the 3 did not. Again, with numbers 30 and 36, we have the prime factorization of 30. We just had that, so we'll just borrow with what we know. I think so too. So then 36 would be 2 and 18. 18 is 2 and 9. 9 is 3 and 3. So here again, we have the 2's match up, but there's no other 2 here. But we have these 3's, and the 5 and 3 are left on their own. So then what matched was the 2 and the 3. 2 times 3 is 6. This is the greatest common factor. And this is true because we had, oh golly gee, yep, 30 and 36, where the greatest common factor between the two was the 6. So you can find it either way, whatever suits your mathematical ergonomics, whatever fits you. So, with an expansion on that, for given 24, that's not 24. If we are given 24, 30, and 36, and we just found out the prime factorization of 30 and 36, which was 2, 3, and 5, 2, 2, 3, 3. And the prime factorization of 24 is 2 times 12. 12 is 2 times 6, and 6 is 2 times 3. So between all of these, we have the 2, and these two have that in common, but this one does not. So we do not have any more 2's in common. We have this 3 in common, but no 5 and no extra 3. So again, our greatest common factor here is that 6. And because mathematicians like to be rigorous, we will do one more example of 15, 30, and 45. Now we are given nothing we already knew, so we get to start from scratch. Just about. So 15 we know is 3 times 5, both of which are prime. 3 is 2, or we just had 30, my mistake. 2 and 3 and 5, and 45 is 3 times 15, and 15 is 3 times 5. So here we get that 3 and we get that 5, but nothing to go with that other 2 or 3. So here we get the 3 times the 5. The greatest common factor is the 15. Nice and easy, I suppose. Then so another example, and this is a special example compared to the others because we have some number of 30 and 49. Ho ho ho, we took a left turn. So 30, the prime factorization is 2 times 3 times 5, as we know and we know and we know. 49 is divisible by 7, 7 times 7. So it only has a 7 in its, or 7 times 7, excuse me, in its prime factorization. And notice that none of this has anything in common. So that means their greatest common factor is 1. Because only 1 can divide into 30 evenly and divide into 49 evenly between these two numbers. Yeah. Kind of like how, and one more example, we have 15 and 28. So 15 was 3 times 5, 28 being 14, and 14 being 2 times 7. The 3 and the 5 have nothing to do with the 2's and the 7. So again, the greatest common factor is 1. They have nothing else in common. All right. Now, going forward will simply be examples. There are a slew of examples provided in the textbook. I'm only going to do 1 out of every 3. So I'm going to do number 3, number 6, number 9, and so forth. I know that doesn't mean a whole lot to you because you don't see the book, but that cuts down on it quite a bit. So number 3, it says to find the prime factorization of 30. Oh, heaven forbid, we just did that how many times? So 2 times 3 times 5. 6. We find the prime factorization of 42, which 2 times 21 is 42. 21 is 3 times 7, both of which are prime. I know this is more visually intuitive, and if you had this on mute, would make no sense. But we just divide this number by a prime and by a prime until we are left with a prime, as shown in a previous example. 9, the prime factorization of 70. So 70, I'm going to use the tree method in this particular example, is 7 times 10. 7 is prime. 10 is 2 and 5. 2 and 5 are prime. So 70, the prime factorization is 2 times 5 times 7. prime factorization of 100, well, we know 100 to be 10 times 10, and 10 is 2 times 5 and 2 times 5. And so we have a 2 and a 5 and a 2 and a 5. We have two 2's, so we're going to use exponential form. 2 squared times 5 squared. Number 15. We have the number 315. And 315 we know is divisible by 9. So 9 can fit into 30 3 times. 31 minus 27 is 4. So that'd be 45 divided by 9 is 5. 35 is divisible by 5 and 7, which are prime. And 9 is divisible by 3 and 3, which are then prime. So we have two 3's, so 3 squared times 5 times 7. That is the prime factorization of 315. And last problem of this example, we have 132. Which 132 is divisible by 11 and 12. 11 is prime. 12 is divisible by 2 and 6. 2 is prime. And 6 is divisible by 2 and 3. And they are prime. We have two 2's, so 2 squared times 3 times 11. All right. Now, the reason why I wanted to do the examples in the homework exercises here is because these particular exercises coming up. That is where it explains in later mathematical courses, you often will want to find factors of a number with a given sum or difference. The following exercises this technique. So that means, number 21, we are to find So we are to find two factors of 24 with the sum of 10. So factors of 24, and I'm going to list them in this way, and it'll help understand why, it'll help us to find the sum of 10. So 1 and 24, we have 2 and 12. We have 3 and 8, and 4 and 6, no 5s, and then 6's come back around. And it said the sum, so if you were to add each of these pair of factors, and that's what we're looking for, 1 and 24 is 25, so that is not 10. So 2 and 12 is 14, also not 10. 3 and 8 is 11. We're getting closer, but also not 10. But 4 and 6 is 10. So the factors we are looking for are 4 and 6. $24. All right, so finding two factors of 30 with a difference of 1. So 30, we have 1 in itself, 2 and 15, 3 and 10, 4, 5, and 6. So 30 minus 1, because we are subtracting the smaller from the bigger in this case, because we're looking for a positive answer. 30 minus 1 is 29. It's not what we're looking for. 15 minus 2 is 13. Also not what we're looking for. 10 minus 3 is 7. Closer, not quite. 6 minus 5 is 1. So what we have looked for, we have found to be 5 and 6. All right, and then for the next few exercises, to find the greatest common factor of the following group of numbers. So for number 27, we are given 10 and 15, and we're to find the greatest common factor. Now I'm going to use the prime factorization in this problem, and then I'll probably alternate between problems finding the greatest common factor. Depending on how you felt most comfortable, do what you will on each problem. And probably good for good practice, if I do the prime factorization, you should just do the general factoring, finding the factors of. So if we compare answers and we both get the same answer, we have done it ideally very correct. And if not, you'll find that I may have made a flaw, or you have made a flaw, and we learn from our flaws faster than our successes. So 10, prime factorization, is 2 times 5, and 15 is 3 and 5. They have the 5 in common, so the greatest common factor is 5. Oops. Sorry, number 30, that offers us 22 and 33. Factors of 22 are 1 and itself, and 2 and 11. There's no 3, 4, 5, 6, or 7, or 8, or 9, or 10. Come back to 11, and that's all of them. 33 is 1 in itself. No 2s, but we have 3 and an 11. And no 4, 5, 6, 7, 8, 9, 10, but we come back to an 11. So we have the 1s in common and the 11s in common. But we have the 11s, which are bigger than 1. So our greatest common factor here is 11. We are given 18 and 24. 18 has a 2 times 9, and 9 is 3 times 3. 24 is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. So then we have this 2 and these 3s, and then nothing matches between those 3s and 2s. So 2 times 3, the greatest common factor is 6. We are given 12 and 48. So 12 is 1 in itself, is 2 and 6, it's 3 and 4, and 4 and 3, and so on and so forth. Comes back around. 48 is 1 in itself, it's 2 and 24, 3 and 16, 4 and 12, no 5s, we have a 6 and an 8, no 7s, we have an 8, and we've come back around. So then we have the 1, the 2, the 3, the 4, no, let's see, we have the 12s, way the heck over here, and we have the 6s, but I do believe that the 12 is the biggest number in common with the both. So the greatest common factor here would be 12. $39, we are given 105, 140, and 175. Okay, so 105 is divisible by 5, which would be 21. 21 is divisible by 3 and 7. 140, also divisible by 14 and 10. If we were to use the tree method, if I may. Because it is intuitive that I can see 14 times 10 is 140. 10 is 2 and 5, these are prime. 14 is 2 and 7, and these are prime. So we have 2 and 2, 5 and 7. And 175 looks to be divisible by 5. 5 can fit into 17 3 times. 25 would be 5. 5 is prime. And 35 is 5 times 7. So we have 2 5s and 7. And then we have this 5 in common and this 7 in common. But nothing for the 3 or the extra 2s or 5. So 5 times 7 is the greatest common factor. It's 35. Okay. So then we have 42. To be the last one of these, we have 36 and 72 and 144. 36 is 1 in itself. 2 and 18, 3 and 12, 4 and 9, 5, 6s, and it comes back around. 72 is 1 in itself. 2 and 36. 3 and 24. Sorry, it took me a moment. 4 and 18. No 5s, we get a 6 and a 12. It's no 7s, but we get an 8 and a 9. Now, if I may recommend at this juncture, finding all the factors of a number takes much longer than just the prime factorization. You take all the pieces and pull them all apart, and there's only so many. And there's only so many that match. And you multiply it out, and you'd be done. But now we get to figure out through everything a number has. So 144 is 1 in itself. 2 and 72. 3. Yeah, 3 can fit in there. Oh, golly gee. So 144 divided by 3. Get into there. 4 times 12, 24. So 8. Excuse me, 48. We have 4. So if we were to have divided by 4 instead, it'd be a 3 and 12. 24, which would be 6. 36. No 5s. A 6 can fit in there though. 144 divided by 6. In there twice. 12, 24, 4. No 7s, but you can get an 8 in there. If this was 8 instead, this would be 1 minus 8. 14 minus 8 is 64. So it'd be 18. You can get a 9 in there. You can see how this is still going. So 144 divided by 9. You get 16, you get 10, 11, you get 12, and 12 times 12 is 144. So we have come to the end of this list. We have ones, we have twos, threes, fours, no fives. We have sixes though. We have nines. We have 12s. We have 18s. Yes, we do. And we also have 36s. And 636 is what it is. That has to be, because it gets no bigger than 36 for the factors of 36, equals 36. So that's 42. Got one more problem. We have just enough time to finish it too. So this is a word problem, so give me just a moment. Excuse me, I have made a typo. Trying my best, sorry. Oh, golly gee. Take me the rest of the time just to write it. Both be off. So, this problem reads, Tony and Delilah both work the night shift at the steel mill. Tony has every 6th night off, and Delilah has every 8th night off. If they both have August 1st off, when will they both be off together again? So, we have August 1st. They are both off. So this is to say 6 days later. So, let's see, 1 plus 6 is August 7th. Tony has off, but Delilah does not. But 8 days later, which would be August 9th, Delilah has off. That's not an increment of 6 for Tony. So this question is actually asking for the least common multiple, which is a funny thing to ask for. having just taught us to find the greatest common factor. So, how this do? So we have numbers 6 and 8. So the next multiple of 6, well, 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, 6 times 4 is 24, 5 is 30, and so on. So now we compare that 1 times 8 is 8, 2 times 8 is 16, 3 times 8 is 24, 4 times 8 is 32, and 5 times 8 is 40. And what we have, finding the least common multiple, so anything closest to what we were given as possible, the closest we found is this 24 and this 24 that match. So they would both be off when August 1st, 24 days later, would mean August 5th. 25th, sorry, is when they will have the same off day again. And we will get into why that is at a later date. I would like to highlight on a previous problem before we move on and cut out, and I know we're over time. I had gone through the problems. Let me see, get that all backed out, because we get there. Yes, no, maybe so. Okay, so went back through some problems. 1 through 9 was fine of chapter 1. However, I did find on number 29, I misled you, and I am so sorry. I'm going to correct this. So what we were asked is to find the area of the figure where this side is 5 inches, this is 3 inches, 2 inches, 1 inches. Because this is 5 and this is 2, this is 3 inches. And I forgot to address this side because this is 3 inches and this is 1. This is 2 inches. Put in parentheses because we found it, we were not given it. So what that means is instead of this 3 times 5 plus 2 times 1, it should have simply been 5 times 2 plus 2 times 1. So 5 times 2 is 10. 2 times 1 is 2. So that would have been 12 inches squared. Now, if you still kept, this is correct. If you still kept with the 3 times 5, understand that it is coloring in this area that doesn't exist. So what we're given on that is we are now taking away this 3 by 1 inch. So 3 times 5 is 15, minus 3 is 12 inches. So this is a reading error, a notation error. I did not read the problem correctly, and this is why we go through and check our work, not just against the answers in the back of the book, but make sure we have done it right. And there's at least 2 ways to do a thing, so might as well try both to make sure that those numbers match. Yeah. Other than that, we will go over the fraction basics next time. Bye.